have homework 20 here, problem 1, and this is another rigid body kinetics problem. We have this uniform cylinder rod of 1.25 meters with a mass of 8 kilograms, and it's laying on a frictionless surface, so maybe like on an air hockey table kind of deal. And this force of 129 newtons is applied at end A. It's starting at rest. I don't know if I've mentioned that, but it is. We're going to find the acceleration of point A and the acceleration of point B. So here we go. We've written this problem out nice and neatly. And I think I'll start by getting the mass moment of inertia of the rod about the center, which is going to be AB right there. This is a cylinder rod, 1/12 ml squared, so 1/12, the mass is 8, length is 1.25 squared, and I already have the numbers, so that should make this a little faster, and these units are kilogram meters squared. I will draw now the FBD and the IBD of this, so we'll go to FBD and IBD, and I think I'm going to make them upright, so I'm looking at the XZ plane here. And making this, labeling this, or applying the stuff that's happening to it is really the main thing that's going to get us where we want to go. All right, so here is there's P being applied to it, and that's the only force that we're going to see in this direction, in this plane. All right, so the accelerations, we should do it based on the center right here, right? So we're going to have an acceleration of the center. It's going to be mass of the whole thing times acceleration. I'm going to call that point G, by the way. It's where the center of gravity. It's just a good place for it. And so that's going to be G in the X direction. We note that there's no forces in the Y direction, or the Z direction, I guess we would call it here. Yeah, the Z direction. So there's not going to be any acceleration in the Z direction. That's just a thing that we would definitely know for sure, right? So, but there is going to be an angular acceleration, alpha. I guess I'll call it AB because I call it AB up above. So we're going to take the sum of the moments, and let's take it about G, right? So in the special case, when we have it about G, we don't have to do the effective moments. We can do it about the center, which is about what that line means, and I'll keep it. I guess I'll leave out the AB there, because this is sort of like generic, okay? Times there. All right, so we could say that the moments that we're going to experience, and counterclockwise is positive. It's going to be this force times that distance. So that's going to be 125 times the length over 2, right? So this is L AB over 2, right in there. So that length is 1.25 divided by 2. And that's the only moment, right, that's happening onto this thing. And it should be negative because that's counterclockwise is positive. So we're going to end up with a negative I, which we said was 1.042 times alpha. So we're able to find what the alpha is going to be. And I believe I get 75. And these are radians per second squared. Now I can also find what the acceleration is going to be, because I can take the sum of the forces, because we could treat it like a particle when it comes to the translation part of it. Sum of the forces in the x direction is equal to mass times acceleration in the x direction. So we have 125 could just put this over to the side. Could have moved this over to the side. I don't know why I didn't. 125 positive, that's the only thing on the left-hand side, is going to equal to the mass of the thing, 8 kilograms, times the acceleration in the x direction. So we can have the acceleration in the x direction, 15.63 meters per second squared. It's a pretty easy problem, by the way. Next problem's much harder. And now we want to try to find but we were looking for the acceleration at A and B, but we have these two pieces of information. We have this and this. So we could draw our 3 diagrams. I might move it over to the left just a little bit. I guess it doesn't matter. That he's all the same length. He got longer somehow. There you go. Set them equal plus, right? So the one that we know is this guy right there. That's the acceleration of g. I could get rid of the x direction. I don't necessarily need to have it. This should have been g. GX, I guess. GX. There you go. And so here GX, I guess I'll leave it there. Now we have the X. Now I'm going to use this same diagram for both points A and B, right? So I'm going to guess the acceleration of A is in that direction. And why not? I'll keep it this way. Let's take the acceleration of B in that direction. I happen to know it's not. But I'm going to start with the acceleration of A is going to be equal to the acceleration of the known thing. So we put the known thing in the second diagram. And actually put it on all 3 spots. Because this is the translation one, right? So this one is moving the thing, and then this one is going to be pivoting about the known spot. So it's actually, in this case, right there. And we do know that it's got an alpha in that direction, right? We just found that alpha in that direction. So we're going to have right up here, I'm going to call this the acceleration. This is A with respect to G in the tangential, and similar but different acceleration of B with respect to G tangential. So the acceleration equation, remember, let's write it for A first. The acceleration here is acceleration of G as a vector, so I'm not making it X right there, plus the acceleration of A with respect to G tangentially plus acceleration of A with respect to G normally. But we know it's not rotating. It doesn't have an angular velocity. It's on the verge of moving, so that's 0. That makes it very easy. And so in the x direction, maybe and I usually write that down, right? The x direction. We get acceleration of A is equal to the acceleration here. So it's going to be this 15.63. And then this one, we can see that this is going to be positive because that's clockwise, plus that alpha, which we know, 75, times the length over 2, 1.25 over 2. So we get, I guess I'll just write it over here, 62.5. And these are meters per second squared. We can do the same thing. Let's see, I'll move this down here. Okay, there you go. I don't have to move my keyboard if I do that. We'll do the same thing here for B. It's the acceleration of B is equal to the acceleration of G That's the known reference, plus the acceleration of b with respect to g, tangential, plus the acceleration of b with respect to g in the normal direction. Recognize that's 0. So I take the acceleration of, I should write x direction again. Be consistent. These are the main equation as a vector. Here it is as a scalar in the x direction. And we're going to equal to plus 15.63, but then minus, because that's the way this arrow is going because of that time right there, minus our 75 and 1.25 over 2. All right, so it's that angle times that length right there. Angular velocity times that length, angular acceleration, excuse me. And I'm going to end up with a negative 31.25 meters per second squared. So the answers acceleration of A is equal to 62.5 meters per second squared that way, and B, acceleration of B is equal to 31.25 meters per second squared that way. I don't know. Maybe this was too easy of a problem. I've asked this problem on exams before. I know that. It might be even a practice problem for the exam. I think it is. Maybe you should know how to do it then. There you go.